We'll do a few more of these little minis. There's so many possible estimation techniques out there, but good news, you've paid the fixed cost of learning R. You're going to see your investment really pay off. Going forward, you'll regularly read about a research project that's using what is essentially effing magic procedure. You have no idea what it is, but it looks good. Maybe a couple other people take it up. You say, wow, that sounds really impressive. Maybe these folks are really talented. They must know a lot. But simple fact is, whatever effing magic they're doing, there's just a package on R that does that. And it probably has a similar format to the LM call that we're now so used to. A lot of packages are written that way. So you get the package, code it as usual. The main challenge is just interpret what the output is. You don't have to know all the details. I mean, I don't want to encourage you to just go off without understanding. Don't be a tool. But don't be intimidated either. They're not better or smarter than you. There's no reason to believe their results because they've got some fancy procedure. Don't believe that it signals something more than, hey, somebody figured out how to install another package in R. We do the usual setup. We take the data, we split it into a training set and a test set. The training set, as it sounds, is what we're training the model on. Training it to recognize certain variation and associate those bits of variation with certain outcomes. We estimate the model on the training set. Then we try it out in the test set, which we kept back, don't let the model see. That allows us to judge how well the model can explain new data. One of the common problems we encounter is the procedures might overfit the training data and completely collapse when looking at the new data. With some procedures, there's cross-validation, where we take the training set and don't even use the whole training set, but randomly select parts of the training set to then estimate the model. Do that a bunch of different subsets of the training set to find the best parameter. So splitting the data multiple ways to estimate different parameters that estimate different parameters, completely demolishing any test of statistical significance. Our p-values are not at all accurate in this case. You know, I first wrote that statistical significance cannot be used here, but then I realized, well, plenty of people do, in fact, use p-values for these kinds of setups. They should not, however. You actually did quite a lot of poking around before coming up with a final model, and so the p-value is going to be completely inaccurate. Typical OLS regression we've been doing is try to explain the average outcome, the average predicted value, conditional on the x variables. But we could also be interested in predicting the median instead of the mean. Or if the distribution is very skewed, if we're interested in tail outcomes, then we could try to predict maybe the 75th percentile, the 25th percentile, or some other value. This chart shows wages by age for full-time, year-round workers with a 4-year degree to show the heteroscedasticity that we talked about earlier. The plot shows the 10th, the 25th, the 50th, the 75th, and the 90th percentiles at each age. You can see the spread gets greater as people age, and the gap's not symmetric. The lower percentiles are flat, but the upper percentiles quite a bit. This might be a good use for a quantile regression. Roger Conker is the econometrician who figured out most of the details. It's pretty computationally heavy. Recall we talked back when we first were doing OLS, figuring a formula for where x squared has a minimum, that's pretty easy. Just take the derivative. But figuring out where the absolute value has a minimum, that's tougher. But the computer can do that work. There's plenty going on underneath the formula, but it's easy in R. Instead of LM, we use RQ, which is regression quartile. It couldn't be QR because that's a term from linear algebra. No, Roger Conker, like Yoda, doesn't talk. In R, we just set the percentiles we want to estimate, and then the rest of the syntax should look pretty familiar. Here's an example of some of the results of the estimation. You can see it does a pretty good job of representing the spread of outcomes.